Very good morning, students. For this lecturing video session, I am going to start the next chapter of 5th unit, which is nothing but dynamics of rigid bodies. So dynamics of rigid body is further divided into two parts. That is kinematics of rigid body and kinetics of rigid body, right? So in the previous unit, that is unit 4, then what we saw was the dynamics of particles, right? So the rotation of the body has been ignored as far as dynamic of particles concerned, which results the simplification of problems. But in practice, that is in practical life, such simplification is not always possible. In machine tool structures, problems involve motion of machine parts connected together by means of links or gears, etc. The motion of one point related to another point is the same body becomes important. Hence, it is necessary to consider the rotation of the body also. So, in this chapter, see, the kinematics and kinetics of rigid body will be covered in detail, right? So, the kinematics of body is the study of geometry of motion of the body, that is position, velocity and acceleration. So, when you talk about acceleration, it's both linear and the angular with respect to time without considering the cause of motion, right? This is kinematics. When you talk about kinetics, the kinetics of the rigid body is also dealt with the geometry of motion with respect to the cause of motion, which is the force for translation and moment due to the force for rotation. Okay, fine. Plane rigid body motion. So in this lecture video, I am going to cover the kinematics of rigid bodies. So in the next lecturing video, I will give a detailed lecture on the kinetics of rigid bodies. Okay. For this video, I am focusing on the kinematics of rigid bodies. A rigid body is said to be motion if the position of any particle of the body or the orientation of any line drawn on the body is changed during a finite time interval. If each particle of the body remains at a constant distance from a fixed reference plane during the motion, it is said to be plane motion. Got it? Okay. So there are three types of plane rigid body motion. That is the classification of the plane rigid body motion are of rigid body. That is the kinematics of plane motion of the rigid body is nothing but the change in the position of a particle in a body or when the lines drawn through the points in the body change their orientation during a period of time, then the body is said to be in motion. During that motion, each point in the body moves to the constant distance measured from the reference plane, and this is called plane motion. So the plane motion of the rigid body can be classified into three. The first one is plane motion of a rigid body in translation. Plane motion of a rigid body in translation. The second one is rotation about a fixed axis. That means plane motion of a rigid body rotating about a fixed axis. And the third one is general plane motion. So the three types of plane motion of the rigid bodies are plane motion of a rigid body in translation, plane motion of the rigid body rotating about a fixed point, and general plane motion. Fine. So let me just give a detailed explanation on the translation. Okay. See, a rigid body is said to be translation if the linear displacement of every point in the rigid body is the same. That is, the orientation of any line drawn on the body remains unchanged, but its position is changed. Okay, a straight line passing through any two of its particle orbits remains parallel to initial position, but the paths of the particle can be either parallel straight line or congruent curves. If all paths are parallel straight lines, the motion is said to be rectilinear translation. So assume a body. So this is the initial position. Let me take this is initial position. This I am going to talk about the rectilinear translation. So this is the initial position. Let me just take 3 points. That is initial positions, right? A, B, C. Right. So assume this is a final position. Let me just consider this as A dash, B dash, and C dash. So from the initial position to the final position is moved. So this is final position. If all the paths are parallel straight lines, the motion is said to be rectilinear translation. Right. Suppose if the paths are concurrent curves, then that would be the curvilinear translation. Let me just draw a drawing so that you can easily understand about this. This is curvilinear translation. See, as far as the translation is concerned, it is divided into two, that is rectilinear translation and curvilinear translation. The initial positions, let me consider 3 points. This is A dash, B dash, C dash. So if the path is in curved form, this is the motion. So from initial position to the final position. Okay. So if the paths are congruent curves, the motion is said to be curvilinear translation. So in the both cases, that is rectilinear and the curvilinear translation, all the particles have the same values of displacement, velocity and acceleration. In both the cases, that is rectilinear and the curvilinear cases, all the particles have the same values of displacement, same values of displacement, velocity and acceleration. Okay. So I have taught you the types of rigid body motion. One of the first one is the translation. Within translation is be divided into two. The first one is rectilinear translation, the other one is curvilinear translation, right? So let me just move to the next one, which is nothing but the plane motion of the rigid body rotating about a fixed axis. That is nothing but the rotation about a fixed axis. Right. Say a rigid body is said to be in rotation. Right. If all the, see, as far as translation is concerned, the body is said to be in translation. That is a linear displacement. When you talk about rotation, this should be, the rigid body should be rotate, right? If all the particles of the body move along this circle centered on a fixed axis called axis of rotation, right? The planes of the circular paths are perpendicular to the axis of rotation, so the rotation and the angular motion about the axis of rotation, right? So let me just draw a drawing so that it would be easy for you to understand it. A body, a rigid body, initial position A, B and C. So this is the initial position before the rotation. So when it rotates, the final position could be something like this. This is B dash. So A dash and B dash, sorry, A dash and A are in the same position because it's rotating about the fixed axis, right? And C dash. So the position could be in this way, and this could be in this way. Okay. So the common center of the circular paths may be located either within the body or outside the body. So as far as this diagram is concerned, the common center of the circular paths is located within the body. So within the body, right? This is the rigid body. So within the body, the center is there, right? Right. And suppose the center is outside of the rigid body, then assume this is a center. Let me just take this as O. This is a common center which is away from the or outside of the rigid body. So let me just take 3 points A, B, C. So as far as this one is concerned, this is the final position, right? So as far as this diagram is concerned, this is the initial position. When it rotates about axis, so this is the axis, so which is the axis is away from or the outside of the body. So point A, that is A dash, B dash and C dash. So this is how the rotation the took place. So this is the final position. So in this motion, as far as the rotation about a fixed axis is concerned, in this motion the particles of the rigid body move in concentric circular path, right? The common center of the circle may be located within the body or the outside of the body. The particles of rigid body moving along the curved path parallel to each other. Okay, so this is the brief idea about the rotation about the fixed axis. So the third subdivision of the plane motion of the rigid body is general plane motion, isn't it? General plane motion. See, as far as the rotation about a fixed point is concerned, the particle located on the axis have zero velocity and zero acceleration as far as rotation about the fixed axis is concerned. Right. So now the third one is general plane motion. Okay. So let me just draw a diagram so it would be easy for you to understand it. Suppose a circular body. Okay. Center as O. This position, initial position, let me just consider this as A, and it rolls on a horizontal plane. This is the final position. So let me just take this O dash and the position as A dash. Right. See, the rigid body is said to be in general plane motion if it undergoes a combination of translation and rotation. Translation and rotation. Right. A rigid body which is neither a pure translation nor a pure rotation, that is called general plane motion. So a rigid body which is neither a pure translation nor a pure rotation, that is said to be general plane motion. So all the particles of the body translate through some distance and also rotate through a certain angle. So the general plane motion is a rotation with translation motion. A general plane motion can be analyzed as a combined motion of translation parallel to the fixed plane and a rotation about the axis which is perpendicular to the fixed plane. Right. So let me just consider this as a example. So let me just take this as rolling wheel as example for the general plane motion. So this slide, let me just cite another example, which is the sliding rod. So this is fixed. So the initial position of the sliding rod is in this manner. Okay. So let me just consider this as A and this as B. So when it slides, the position could be changed. So this could be A dash and this could be B dash, and the motion takes place in this direction. So and the center is somewhere here. So in this, in the figures, the motion can be taken as a combination of translation of the ends and rotation about the axis passing through the O and the perpendicular to the XY plane. Right. So the motion of the rigid body is said to have general plane motion, with the body undergoes a combination of translation and rotation. Examples of the general plane motion, this is a rolling wheel or the sliding rod or the connecting rods of the reciprocating engine also can be cited as an example for the general plane motion. Okay. So in the next one, what I'm going to do is now I'm going to draw give some formulas for the kinematics of the rigid bodies. Okay. So this is nothing but the comparison between linear motion and angular motion. Okay. So first one, let me just as a point of comparison. Linear motion against angular motion. Angular motion. Okay. So let me just about table. So which would be you would be in a position to understand in a detailed manner. Okay. So first let me just draw this serial number also. Let me just include it. So first one, let me just cite as a displacement. See, as far as the linear motion is concerned, usually it is denoted with S, right? So when it comes to angular motion, this is the linear displacement is mentioned as S. When it comes to the angular displacement, it is denoted with theta. The next one is initial velocity. See, as far as the linear initial velocity is concerned, it is denoted with small u. When it comes to angular initial velocity, it is omega o. The third one, the final velocity. Final velocity is mentioned in linear, that is linear final velocity is mentioned small v, and as far as the angular final velocity is concerned, it is omega. Then the fourth one, acceleration. So acceleration, see, the linear acceleration can be denoted with small a, and the angular acceleration is denoted with alpha. The fifth one, time taken. So in both cases, the linear as well as the angular motion is concerned, it is denoted with small t only. Okay, right. So the sixth one, the mathematical expression of velocity. Mathematical expressions of velocity. See, as far as the linear motion is concerned, the small b is equal to ds by dt. When it comes to angular, so omega equal to d theta by dt. Okay. So when you write the mathematical expression for the acceleration, so a is equal to dv by dt. That is equal to, so v is nothing but ds by dt. That is d square s by dt square. Similarly, for the angular motion, the acceleration can be denoted as alpha is equal to d omega by dt equal to d square theta by dt square. Okay. So next one, the equations. Equations of motion. First, let me just consider there is a uniform velocity. For the linear motion, it can be denoted as S is equal to Vt. When it comes to the angular motion, this can be denoted as theta is equal to omega t. Okay. Next, the uniform acceleration. When it comes to the uniform acceleration, the formulas for the linear motion can be v is equal to u plus at. Similarly, for the angular motion, it can be denoted as omega is equal to omega o plus alpha t. The second one, s is equal to ut plus of at square. So theta is equal to omega o t plus of alpha t square. The third equation with the uniform acceleration v square is equal to u square plus 2as. So here, as far as the angular motion is concerned, omega square is equal to omega o square plus 2 into alpha theta, right? So the last one, there is a displacement in nth second. So which can be written as, so displacement can be mentioned as yes, so it can be written as u plus a by 2 into 2n minus 1. So when it comes to angular motion, so theta nth second is equal to considered as omega o plus alpha by 2 to 2n minus 1. Okay. So omega is nothing but, the omega o is the initial velocity, the initial angular velocity of the body, right? So omega is mentioned in radian per second, omega o or omega, okay, radian per second. When it comes to r, which is nothing but the radius, right? And v is nothing but the linear velocity, that is a linear velocity of the body. U is the, S is displacement, U is initial velocity, F is final velocity. So to theta is the angular displacement, right? Fine. So S is mentioned in meter, right? S is in meter, and this is units. Okay, so W, the units, this is let me just consider this way. S is equal to in meters, so this is unit, and theta, it can be mentioned as in radians. Okay, and as far as alpha is concerned, which is radian per second square, and the linear acceleration is mentioned by meter per second square. And u and v, u or v, that is initial velocity or the final velocity, can be the unit of the initial velocity and the final velocity is meter per second. This is the units. Okay, so this is the comparison between the linear motion and the angular motion. So next one, let me just give a relation between the linear motion and the angular motion. So relation between linear and angular motion. Okay. So first relation, that is a between linear displacement and the angular displacement. So linear displacement equal to angular displacement, it's a product of angular displacement and the radius. So S is equal to angular displacement, which is, sorry, correct, angular displacement is S, not linear displacement, yes, and the angular velocity in terms of theta, isn't it? Theta into r, right? S is equal to theta into r. The second one, so S is linear displacement, theta is the angular displacement, and radius is determined r. So next one is the linear velocity, the relation between linear velocity and the angular velocity. Linear velocity equal to the product of angular velocity and radius. So linear velocity can be mentioned as v equal to, angular velocity is omega, into r. So this is the next relation between linear motion and the angular motion. The third one, nothing but the acceleration. That is linear acceleration equal to angular acceleration. That's the product of angular acceleration and its radius. So this can be denoted as linear displacement can be mentioned as A equal to alpha into r. Okay, so this is the relation between the linear and the angular motions, right? So let me just solve a problem for using the kinetics of particles. Okay, so the problem one: a wheel rotating about a fixed axis at 25 rpm is uniformly accelerated for 60 seconds, during which time it makes 60 revolutions. Find 1. Angular velocity at the end of this interval. Second one, time required for the speed to reach 120 rpm. So first let me just take the given data, that is the to extract the as much as information available here. A wheel rotating about a fixed axis at 25 rpm, which is nothing but the initial speed. So NO equal to 25 revolution per minute. RPM is nothing but revolution per minute. If it is mentioned RPS, then revolution per second. Okay. So uniformly accelerated for 60 seconds, which is nothing but T is equal to 60 seconds. Right. During the time it makes 60 revolutions. That is revolutions equal to 60. Right. So to find, so what are the things? First, from the angular velocity, which is nothing but the angular velocity is nothing but the omega, isn't it? Right? And time required for the speed when the speed reaches 120 rpm, what is the time taken? T is equal to what? So solution. So one revolution equal to, usually it needs to be converted into radian. So one revolution equal to 2 pi. So in radiant. Okay. So when it for the 60 revolutions, then when it is for 60 revolutions, then 2 pi into 60. So use the calculator. 2 into pi into 60, which works out 376.9. And so let me just take this as 377. The unit is in radian. Okay. Right. So the angular, this is the angular displacement. So this is nothing but the angular displacement equal to 377 radian. So angular displacement, what I have taught you. So this is the linear displacement. This angular displacement is nothing but the theta. So this can be denoted as theta. Okay. So the initial angular velocity, which is omega O. So initial speed, it was 25 rpm, revolution per minute. So the formula for angular velocity is 2 pi n by 60. Right? N is nothing but the speed, right? Therefore 2 pi into the initial the speed was 25 divided by 60, which is equal to 2 into pi into 25 divided by 60, which works out 2.62. 2.62. The unit of this one is radian per second. Okay. So I have taught you the several formulas for the angular motion, isn't it? So I am going to use this formula, that is theta is equal to omega O t plus half into alpha t square. So using the equation theta is equal to omega O t plus half alpha t square. So theta known, so 377, omega O is known 2.62, and the time was 60 seconds, isn't it? Time was 60 seconds into 60 plus half into alpha t is 60 square into 60 square. So 377 equal to, so just use the calculator, 2.62 into 60, which is 157.2 plus 0.5 alpha into 60 square, which is 3600. So 377 equal to 157.2 plus into 0.5, which is 1800, right? 1800 alpha. So let me just consider this as in the this side. So 377 minus 157.2 equal to 1800 alpha. So the alpha equal to 377 minus 157.2 divided by 1800. So 0.122, 0.122, the unit of velocity, this is angular velocity, isn't it? So radian per second square. This is this angular acceleration, right? Then what about the what we need to find is the angular velocity at the end of this. So the formula for omega is equal to omega O plus alpha t. So you use that formula here. So omega equal to omega O plus alpha t, which is equal to omega O is 2.62 plus alpha is 1.12 into 60, which is equal to, if you just use the calculator, 2.62 plus 0.122 into 60, close the bracket, you'll get 9.94 radian per second. So this is for the condition 1. And for condition 2, what the condition 2 says? The condition 2 says time required for the speed to reach 120 rpm. Okay, 120 rpm, the condition 2. So when n is equal to 120 revolution per minute. So you know the omega formula, omega is equal to 2 pi n by 60. So 2 into pi into n is 120 here, divided by 60. Okay, so which is equal to 2 into pi into 120 divided by 60, which works out 12.57 radian per second. So let me just use this formula, omega equal to omega O plus alpha t. So from this formula I need to find the value of t. So omega is 12.57, omega O is 2.62, and alpha is 9.94 into t. So t equal to 12.57. When this 2.62 comes in the left hand side, it will become minus 2.62, right, divided by 9.94, which is, sorry, alpha is wrongly I put it, alpha is 0.122, isn't it? So 12.57 minus 2.62 divided by 0.122, 81.56. So 81.56 seconds. So finally arrived the value for the omega and the time. Okay. Hope you have all understood. First, what you have to do is you have to just memorize these formulas. So this linear motion you would have studied in 4th unit, right? So when it comes to 5th unit, that is the dynamics of rigid bodies. This comes under the kinematics, right? Kinematics of the rigid bodies. You have to remember these formulas, right? Omega is equal to omega O plus alpha t. Similarly, theta and the omega square formula. You have to remember this. And the unit, don't forget this unit. So unit is very essential when you just solve the such problems from the chapter kinematics of rigid bodies. Hope you have all understood how to solve a problem from the kinetics of rigid body, and you have understood the fundamental of kinematics of rigid bodies, right? Thank you.